If you follow Dr. Payam's channel, which you should, you may have already seen his video about the cosine of x equaling 2. Let's find a general solution for the cosine of x equals some complex number z, and then solve it for I. We'll start with z equals e to the ix plus e to the negative ix all over 2. Multiply both sides by 2 and again by e to the ix. Bring this side around here and we end up with a quadratic which we can solve, where a equals 1, b equals 2 times z, negative, and c equals 1. And now let's release the quadratic formula onto this. E to the ix equals negative b plus or minus the square root of b squared minus 4ac all over 2a, which will be negative 2z plus or minus negative 2z all squared minus 4ac all over 2 times a. That's 2z plus or minus square root of 4z squared minus 4 all over 2. But we're going to factor out this 4 and bring it into the front. Let's just do that. Let's take the 4 there. This will become minus 1, and we'll have a 2 here. So finally, our solution for e to the ix equals, these 2's all cancel out, and we have z plus or minus z squared minus 1. Now let's just take the log of both sides. We have ix equals z plus or minus square root of z squared minus 1, the logarithm of all that. Multiply both sides by negative I. So we end up here, x equals negative I log z plus or minus z squared minus 1. And that's all logarithmed there. And here is our general solution for the cosine of x equals z. We can turn this loose on some typical real solutions. Try z equals 0 and z equals 1 and see what you end up with. But I want to try z equals I, purely imaginary, in which case x equals negative I times the logarithm of I plus or minus square root of I squared minus 1. Simplify that, factor out the I here, and now let's take out this imaginary number. The logarithm of I will be I times pi over 2. So now we'll distribute this negative I. That negative I times I pi over 2 ends up being pi by 2. And just bring this negative I over here. Give it a nice box because Bob is your uncle after we add the pi m's.